Hey guys, so I did figure out what was going on with my computer, some updates and a restart, and it was fine. But I pushed the assignment due tomorrow at 10 to 2 p.m. tomorrow because I just feel it's not fair or whatever because it's 3:09 right now and I'm recording this video. It busy day watching my daughter. My wife had to do work, obviously. So I just didn't have time to record. Till now. So I'm recording this. I'm going to show you this video. This video, I'll stop and talk and explain, and then it should help you do the 8 problems 1 through 8 due tomorrow. I'll record another video going over the homework, and then the second part of that worksheet due Wednesday, and then we'll have class. Everything will work properly, and I'll go over that on Wednesday and then kind of summarize concentration and temperature changes, but that's what these videos are on. And then the last part will be pressure, which we'll do. I'd rather do that live in the class. So here we go.
In this lesson, you will learn about how a system at equilibrium responds to changes in temperature. LeChatelier's principle states that a chemical system...
So I'm going to interrupt her. So notice this is balanced. And if you saw me use the ruler with the coins the other day, I think all teachers use the same analogy. So like a seesaw, if it's balanced, it's at equilibrium. But what you're going to see is some A and B here drop out of the sky. So we're going to increase the concentration over here. So this little test tube person is going to slide down here because this side is going to get heavier. So the system will be stressed, not at equilibrium. So what it has to do is shift to the right, make more products to balance out back to equilibrium. So that's concentration changes. She's going to show you temperature changes in this video. And then there's another video that I'm going to show after this that kind of goes through those concentration changes again. So this is all it's going to be. I'm probably not going to use a whiteboard at all because I'm just going to stop the videos here and talk through it. So hopefully I can keep this whole thing around 10 minutes. Here we go.
At equilibrium always works to restore equilibrium when it is stressed. To consider what happens to a system at equilibrium when temperature is changed, you must first consider the energetics of the reaction in question. If the forward reaction is exothermic, then the reverse reaction must be endothermic. Let's examine this hypothetical reaction where reactant A reacts with reactant B to produce product C and product D, with a change in heat of minus 75 kilojoules.
Okay, so that's exothermic, right? Negative delta H means exothermic. So the important thing here is that this energy is written on this side of this equation. So I watched this earlier. I forget if they show that. If they don't, I'm going to have to pause it here.
This means that when the forward reaction occurs, 75 kilojoules of energy is released and 75 kilojoules is absorbed when the reverse reaction occurs. So an increase in temperature would mean that the endothermic reaction would be favored to remove the excess heat, therefore counteracting the imposed stress. Decreasing the temperature would cause the system to produce more energy, therefore the exothermic reaction would be favored. The dimerization of nitrogen dioxide to dinitrogen tetroxide is an exothermic reaction. Nitrogen dioxide is a brown gas, whereas dinitrogen tetroxide is colorless. What observations do you think can be made when the temperature is decreased? How about when the temperature is increased? Please pause the lesson to think about this and resume once you are done.
So I'm, like laughing here because I know if you're watching this, you're like, I don't know what's going on. None of this makes any sense. I get that, right? I know it, and she's not going slow enough, not explaining it very well. I know it, and it's like, it's a little confusing. So let me back up here to this right here.
Exothermic reaction would be favored. The dimerization of nitrogen dioxide to dinitrogen tetroxide is an exothermic reaction.
Okay.
Nitrogen dioxide is a brown gas.
Sorry. There. No. Why does it keep doing that?
Exothermic reaction.
Stop. Okay. All right. So I'm going to stop it here. So I'm going to use this as an example, and I'm going to have to use a whiteboard here to teach this, because if you're just watching this, that's not going to really, you're not going to learn anything. So let's use this exact example. Get a new one here. All right. All right, so if I go back to this, we got 2NO2 yields N2O4. All right, so here we go. 2NO2 N2O4. Now, she said it was exothermic, so my delta H, my energy, would go over here. So here's my energy. Exothermic, it exits at the end. So this is a big deal. If you didn't learn that earlier in the year, then this is like super hard. So if you know it's exothermic, that means the energy goes over here. It doesn't matter what the energy is. It could be 100 kilojoules, 1,000, it could be 50, whatever. So the energy goes over here, okay? So the way I teach temperature, right? So again, let's say we have a balanced scenario, right? Here's our seesaw, products and reactants. Right now we're at equilibrium. Well, if the temperature is increased, right? So if we heat this reaction up, so we increase the temperature. The way I teach this is we treat the energy and temperature, right? Heat. We treat heat, temperature, and energy as all kind of the same thing, which is really dangerous because temperature is just a measure of the amount of kinetic energy, the average kinetic energy. But in this case, I'm going to say, okay, when I heat this entire, let's say this reaction's in a sealed container, and I heat the whole thing up, really what I'm doing is I'm increasing this number. So I'm adding more energy to this side of the equation. So I treat heat and temperature and energy as almost like masses, like things I can pile on this side. So if I add more heat to this side, it's like increasing the number of 8 delta H's, right? So I pile this on. What's going to happen is this product size is going to get too heavy and it's going to go down. So let me kind of do that. So now we're kind of like this, right? Here's my products, here's my reactants. So my products are N2O4 and delta H. So now this side's too heavy. Why? Because I heated it up. And what does that mean? It means I increased the amount of energy on this side. Why? Because that's where the energy is. So energy and heat are related. So if I heat this up, it's like adding more energy here. So my products decrease. Sorry, I should not say that. My products go down towards the ground, okay? So now we are not at equilibrium. We are not at equilibrium. How does it go back to being balanced? Some of the products have to break apart and form reactants. We have to transition, or not transfer some of the products over to the reactant side. So some of this N2O4 would break apart and form NO2. And when it does that, so if some of these products now turn into reactants, eventually we will go back to being balanced at equilibrium. So the stress here is we're increasing temperature. That causes the right side of this to go down. So the equilibrium will shift to the left. And if it shifts to the left, you're going to make more reactants. If you make more reactants, it's going to get heavier, quote unquote heavier. It'll go back down towards the ground and they will balance out. So they will be constant again at equilibrium. So the answer, if this question was, okay, in what direction does the equilibrium shift when you heat this reaction up? It shifts left. Shifts left towards the products. And if you're going towards the product, you're making more NO2, less N2O4. That's why this side, the reactants, will go down and the product side will go up. And it'll eventually be back to equilibrium. I know this is really tough to learn this way, but it's the best I can do right now. Okay, let me go back to the video.
Nitrogen dioxide is a brown gas, whereas dinitrogen tetroxide is colorless.
So she wants to pause the lesson. So if we heat this up, I think she said heat it up. If we heat this up, what color do you think you would see? So if we heat it up, I just went to the blackboard there and I told you we were going to shift left, meaning we're going to make more of this. So I would expect it to get brown or dark or whatever. I think she said heat it up. I can't remember. Sorry. We'll find out.
What observations do you think can be made when the temperature is decreased?
All right, so we're decreasing. Okay, so now it's the opposite. So let me go back to the whiteboard so you're not getting confused here. So now we're going to decrease. So let me erase this. So we would shift right, but let me explain why. So if we decrease the temperature, the exact opposite. Hold on here. Sorry, guys. I'm having technical glitches and difficulties today. Okay. I think I'm just trying to do too much at once here. All right. So in this case, what she just said is we are going to decrease the temperature. So if we decrease the temperature, right? So if we decrease the temperature on this system, that's like removing some of this delta H. So we're going to take some of this off. So if we have products and reactants that are balanced and we remove some of the product, we take some off, like I did the other day with that ruler, right? So if we're here, reactants and products, and I take some of this off, take it off. What's going to happen is that side is going to go up in the air because it's lighter, right? Quote unquote lighter. So how does this reaction shift to go back to being balanced? Some of the reactants must transfer to the products. So when some of the reactants transfer to the products, we go back to being balanced at equilibrium. So that means we're shifting to the right. Shifts right. And according to the video here, this is a colorless gas, and then this is brown, right? So I would expect, I think it was colorless or it was white, I don't know. I would expect to see more colorless gas if I decrease the temperature on this reaction. Okay, let's go back.
When the temperature is increased. Please pause the lesson to think about this and resume once you are done.
All right, so she asked both, decrease and increase. So I know this is tough, but if you are trying to pay attention, hopefully this will make sense. Here we go.
A decrease in temperature favors the exothermic reaction, so more dinitrogen tetroxide is produced. Since it is a colorless gas, the mixture should appear paler. An increase in temperature favors the endothermic reaction, so more nitrogen dioxide is produced. The mixture should therefore appear darker brown. Addition of a catalyst does not affect.
Okay, we'll talk about a catalyst some other time. And I'm changing the game here for a second. How much time has gone by? 13 minutes. That's too long. Sorry, guys. I got to show you one more thing. All right, so everything I just went over, she went over. Hopefully that made some kind of sense. Let's talk about concentration changes too, not just temperature. So let's take a reaction like very simple. Na plus Cl 2 yields 2 NaCl. Two of those. Okay. So if I had this at equilibrium, so let's do this here. All right, and I had some Na here, and I had some Cl2. All right, and I have some NaCl here. Okay. I know it's not balanced. I'm not too worried about that, or is it? It is balanced. Okay. So if this is a concentration thing, if I add more Na, add more Cl2, or add more NaCl, that side will go down, the side that I add more. So if I have some Na sitting over here and I dump it on the reactant side, it's going to do this. I'm going to have too much over on this side and not enough on this side, right? So if I dump this here, this side, the left side, the reactants here, the R's, products, right? Reactants are going to go down. So what has to happen is some of the reactants must react and make products. So if I dump this on here, I add more sodium in here, it's going to disrupt my equilibrium. So some of the reactants must react, make products to go back to being balanced, because it would. Eventually, it would react the excess I added, shift it over here, and be back to being balanced. So that's one example of concentration. It would shift to the right. If I increase my Na or Cl2, we would shift right, making more products. That would get it back to equilibrium. And just one thing in the homework is, if we are shifting right, if we are shifting this direction, you're going to make more of these, of your products, and use up your reactants. And then the opposite is true. If I remove some Na, so if I take some Na, if I erase this here, now what happens if I remove a reactant? It's going to go like this. Our reactants are going to be too light because I just erased them. So now the opposite. Products are going to have to shift towards the reactants, make more reactants to go back to being balanced. Reactants and products will be fairly even there. Not even, balanced or constant. Shouldn't use that word, sorry. So again, if you remove the concentration, remove Na, it's going to shift to kind of fill in what you just took, right? So if we remove Na, then it would shift left. And shifting left means you're going to make more reactants and you're going to use up your products. I know this is tough. Even as I'm doing this, I'm like, man, I don't know how many people are going to follow this, but it's the best I can do right now. I really wanted to do this live and ask questions, see if you guys had questions, but it is what it is. So I'll post this. It's too long, but hopefully you're watching it and doing that sheet due tomorrow at 2:00. All right. I'll see you guys later.